Hi friends, this is the 10th lecture in the lecture series for the preparation of 18 Mechanical Engineering, and today we will be dealing with a concept called the fins, and they are also called as extended surfaces. And these devices come into application whenever we have to enhance the heat transfer from a device to the surrounding. So let's suppose some IC engine is there, and IC engine is there. If we want to enhance the heat transfer between this body and the surface, we have to use the heat transfer equation, that is conversion heat transfer equation. Q dot is equal to H A S into T minus T infinity, and to enhance this Q dot we are having three options, that is either enhance this H, and this can be done by installing some fans or blowers, and this is a recurring cost and it is impractical. So next method is to enhance the T minus T infinity value, and to do that we have to reduce the T infinity value, and this is not impractical. So the temperature of the since the temperature of the surrounding is a fixed value, and let's do the enhancing of this heat transfer by increasing AS, and AS increase is nothing but extended, which is nothing but the increment in the surface area of the device, and this can be done by installing some surfaces and which are called the extended surfaces. And these extended surfaces that are installed in order to increase the surface area, which will further enhances the heat transfer rate by convection, is called the fins. Okay, for the extended surfaces, and these fins are classified into three, and this classification is based on the geometry of this particular fin. So first classification is longitudinal or straight fins, and I will draw the figure so you can understand it clearly. So this is the surface and this is the fin. Okay, so this is nothing but the longitudinal or straight fins. This particular type of fins are called the longitudinal or straight fins. And the next classification is the radial or circumferential fins, and this radial or circumferential fins will be like so. The radial or circumferential fins will be like this. Okay, I hope you people are getting some clarification in this radial type of fins. And next, the last type is the spin fins, or they are called the spines, and these spin fins or spines are nothing but some extended fins or extended pins that are coming from the surface of a particular device or a body. So this is the surface from which the pin fins are extended, and these are pin fins, and this is the radial fins, and this is longitudinal or straight fins. Okay, so these are the three classification of the fins, and let's analyze this fin, that is how the heat transfer is occurring, what is the heat transfer in this particular fins if you are installing these fins. So fin analysis can be done by, or can be done on a particular fin. Let's suppose some surface over here, and let's suppose some tapered pin fin that is present on this particular device or the surface like this. and this is the surface on which the fin is present. And to analyze this fin, we have to consider some element of this fin which is at a distance x and which is having the dimension dx. So before that, this fin is having the temperature T and some fluid is flowing with the temperature T infinity and convective heat transfer coefficient H. So to analyze this particular fin, let's consider this small element dx, small element of length dx, that is that we have got from the element like this, and let's suppose this is the dx distance of or the dimension of this element. Now let some heat transfer by conduction is entering into the element like this, and the heat transfer by conduction that is leaving from the element is qx plus dx, and along with this conduction heat transfer there is some convective heat transfer is occurring, and this small element we are having dq dot conduction. And here we are having the surface area AC, and here we are having the surface area AC plus DAC. Okay, so to analyze this, let's write the energy balance. So energy balance is nothing but all the energy that is entering will be equal to all the energy that is leaving, x plus dx into ds plus dq dot convection. Okay, so these are the two energies that are entering and leaving. So let's expand this. That is, we can write this as minus kc dt by dx will be equal to minus k into ac is changed into ac plus dac into dt by dx is changed into dt by dx plus d by dx of dt by dx into dx plus the convertive term that is h into das into t minus t infinity. Okay, will be so this is the expanded term of this energy balance, and we can rewrite this equation by cancelling the and neglecting higher order terms. Minus kac d square t by dx square into dx minus k into dac dt by dx plus h into das t minus t infinity equal to 0. So this is the simplified equation neglecting all the higher order terms, and this can be further written as, or let's divide the entire equation by minus kac into dx. So we can write this equation as minus kac, this term will be cancelled, and we can write d square t by dx square plus k is cancelled, dac by dx and dac by dx into 1 by ac into dt by dx plus, or rather minus, h by kac into das by dx into t minus t infinity. This is equal to 0, and this is the, and this equation is the most general fin equation. Okay, and let's suppose we are having, let suppose the cross sectional area of fin is not varying, that is AC is constant, and in this particular equation we have considered a tapered fin in which the area of cross section is varying constantly. And for some area or for some fins in which the cross sectional area is constant, we can rewrite this entire equation as d square t by dx square minus, and this dac by dx term will be 0, and minus h das by dx will be the perimeter, and we will be having das by dx is equal to perimeter and dac by dx equal to 0 for this area constant condition. Okay, so we can rewrite this equation as minus hp by kac into t minus t infinity equal to 0. And this, for this equation, let's suppose t minus t infinity is equal to theta and dt is equal to d theta, and we can rewrite this equation as d square theta by ds square minus hp by kac into theta equal to 0. And let this hp by kac is some constant or the fin parameter, that is m square, square root of square of this particular fin parameter, and we can rewrite this equation as d square theta by dx square minus m square theta equal to 0. And this is the general form of fin equation for constant